Prime numbers. Before defining a prime number, let's make note of a few basic facts. Notes. 1. Every integer is divisible by 1. Indeed, if n is an integer, then n is equal to 1 times n. 2. Every integer is divisible by itself. Indeed, if n is an integer, then n is equal to n times 1. 3. It follows from notes 1 and 2 that every integer greater than 1 has at least 2 positive integer factors, 1 and itself. A prime number is a natural number with exactly 2 positive integer factors. Equivalently, a prime number is an integer greater than 1 that is divisible only by 1 and itself. An integer greater than 1 that is not prime is called composite. Let's look at some examples. 0 is not prime because every positive integer is a factor of 0. If n is a positive integer, then 0 is equal to n times 0, so that n divides 0. 1 is not prime because it has only one positive integer factor. If 1 is equal to k times b, with k greater than 0, then k is equal to 1 and b is equal to 1. The first 10 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. 4 is not prime because 4 is equal to 2 times 2. In fact, the only even prime number is 2 because by definition, an even integer has 2 as a factor. 9 is the first odd integer greater than 1 that is not prime. Indeed, 3, 5, and 7 are prime, but 9 is not because 9 is equal to 3 times 3. The first 10 composite numbers are 4, 6, 8, 9, 10, 12, 14, 15, 16, and 18. Let's try an exercise now. This is a good time to pause the video, try this exercise yourself, and then resume the video to check your answers with mine. What are the first 20 prime numbers? Well, we have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, and 71. What are the first 20 composite numbers? 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, 20, 21, 22, 24, 25, 26, 27, 28, 30, and 32. Is 91 prime or composite? Why? Well, 91 is composite because 91 is equal to 7 times 13. Prime number fact 1. There are infinitely many prime numbers. Prime number fact 2. Every integer greater than 1 can be written uniquely as a product of prime numbers up to the order in which the factors are written. The second fact is known as the fundamental theorem of arithmetic. It is used often in many branches of mathematics. As an exercise, use prime number fact 2 to explain why every integer greater than 1 has a prime factor. Go ahead and pause the video now, try to provide your own explanation, and then resume the video to check your explanation with mine. Let n be an integer greater than 1. By prime number fact 2, n can be written as a product of prime numbers. Let p be any of the prime numbers in that product. Then p is a prime factor of n. When we write an integer n as a product of other integers, we call that product a factorization of n. If all the factors in the product are prime, We call the product a prime factorization of n. Let's look at some examples. 20 is equal to 4 times 5. So 4 times 5 is a factorization of 20. This is not a prime factorization of 20 because 4 is not prime. 20 could also be written as 2 times 10. So 2 times 10 is another factorization of 20. This shows that factorizations in general are not unique. An example of a prime factorization of 20 is 20 equals 2 times 2 times 5. We can also write this prime factorization as 2 times 5 times 2 or 5 times 2 times 2. So you can see that if we consider different orderings of the factors as different factorizations, then prime factorizations are not unique. This is why we say that prime factorizations are unique up to the order in which the factors are written. A prime number is equal to its own prime factorization. In other words, we consider a prime number to be a product of primes with just one factor in the product. For example, the prime factorization of 2 is simply 2. Another exercise. Find 4 factorizations of each of the following positive integers, exactly one of which is a prime factorization. Okay, so you'll do 3 factorizations that are not prime and 1 prime factorization. Okay, so now's a good time to pause the video. Try to do this exercise on your own first, then resume the video and check your answers with mine. Note that there may be many correct answers for this. So if not all your answers agree with mine, that doesn't mean that they're all incorrect. Okay, 12 can be written as 1 times 12, 2 times 6, and 3 times 4. Those are factorizations that are not prime factorizations. And a prime factorization of 12 is 2 times 2 times 3. For 18, we have the factorizations 1 times 18, 2 times 9, and 3 times 6, and a prime factorization of 2 times 3 times 3. For 100, some factorizations that are not prime are 1 times 100, 2 times 50, 4 times 25, and prime factorization is 2 times 2 times 5 times 5. Since prime factorizations are unique only up to the order in which the factors are written, there can be many ways to write a prime factorization. As an example, 10 can be written as 2 times 5 or 5 times 2. To make things as simple as possible, we will always agree to use the canonical representation or canonical form. The word canonical is just a fancy name for natural. And the most natural way to write a prime factorization is in increasing order of primes. Some examples. The canonical representation of 10 is 2 times 5, right? We write the prime 2 first and then the prime 5 second because 2 is smaller than 5. The canonical representation of 18 is 2 times 3 times 3. We can tidy this up a bit by rewriting 3 times 3 as 3 squared. So the canonical representation of 18 is 2 times 3 squared. If you are new to factoring, you may find it helpful to draw a factor tree. Let's look at an example. Let's draw a factor tree for 18. We start by writing 18 as the product 2 times 9. We put a box around 2 because 2 is prime and does not need to be factored anymore. We then factor 9 as 3 times 3. We put a box around each 3 because 3 is prime. The prime factorization can now be found by multiplying all the box numbers together. Remember that we will usually want the canonical representation, and so we write the final product in increasing order of primes, 2 times 3 squared. By the fundamental theorem of arithmetic, prime number fact 2, it does not matter how we factor the number. We will always get the same canonical form. For example, here is a different factor tree for 18. We factor 18 as 3 times 6. We put a box around 3 because it's prime. And then we factor 6 as 2 times 3. And we put boxes around 2 and 3 because they are both prime. And notice that we get the same canonical representation, 2 times 3 times 3, or 2 times 3 squared. Now, to show that a positive integer n is composite, we simply need to produce a factor of n that is different from 1 and n itself. This may sound easy, but in practice, as we look at larger and larger values of n, it can become very difficult to find factors of n. As an example, the largest prime number that we are currently aware of at the time I'm filming this video is 2 to the 82,589,933 minus 1. This is an enormous number with 24,862,048 digits. By prime number fact 1, we know that there are prime numbers larger than this, but we have not yet found one. Remember that prime number fact 1 says there are infinitely many prime numbers. Composite number fact 1. If n is composite, then n has a prime factor p less than or equal to the square root of n. Now, the square root of n is the positive real number such that square root n times square root n is equal to n. For example, the square root of 4 is 2 because 2 times 2 is equal to 4. Let's look at an example. Let's determine if 187 is prime or composite. Since the square root of 187 is less than the square root of 196, which is 14, by composite number fact 1, we need only check to see if 187 is divisible by 2, 3, 5, 7, 11, and 13. Those are all the prime numbers less than 14. Checking each of these, we see that 187 is actually equal to 11 times 17. So 187 is in fact composite. Another example. Let's determine if 359 is prime or composite. Since the square root of 359 is less than the square root of 361, which is equal to 19, by composite number fact 1, we need only check to see if 359 is divisible by 2, 3, 5, 7, 11, 13, and 17. A quick check shows that 359 is not divisible by any of these numbers, and so 359 is prime. Another exercise, determine if each of the following positive integers is prime or composite. Go ahead and pause the video now, try this exercise yourself, and then check your answers against mine. As a hint, you're going to go ahead and use that last composite number fact to help you. 119 is composite because 119 is 7 times 17. 437 is composite. 437 is 19 times 23. 541 is prime. 1,231 is prime. And 1,457 is composite because it's equal to 31 times 47. We would now like to verify that there are, in fact, infinitely many prime numbers. Remember, this is prime number fact 1. If n is a positive integer, then the number n followed by an explanation point, that's pronounced n factorial, is defined by n factorial equals the product of the numbers 1 through n. Some examples. 2 factorial is equal to 1 times 2, which is 2. 3 factorial is equal to 1 times 2 times 3, which is 6. And 4 factorial is equal to 1 times 2 times 3 times 4, which is 24. Let's try a few more as an exercise. Compute each of the following. Go ahead and pause the video, try to do these computations, and then resume the video to check your answers with mine. 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120. 6 factorial is 1 times 2 times 3 times 4 times 5 times 6, which is 720. And 7 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7, and that's 5,040. Observe that if n is greater than 2, then n factorial is a number larger than n that is divisible by every positive integer less than or equal to n. Some examples. 3 factorial, which is equal to 6, is divisible by 1, 2, and 3, right? Because 3 factorial is 1 times 2 times 3. 4 factorial, which is 24, is divisible by 1, 2, 3, and 4, because 4 factorial is 1 times 2 times 3 times 4. For n greater than 2, the number n factorial actually has many factors. For example, the factors of 3 factorial, which is 6, are not only 1, 2, and 3, but also 6. And the factors of 4 factorial, which is 24, are 1, 2, 3, 4, 6, 8, 12, and 24. Let's try another exercise. This one's a little harder. Go ahead and pause the video, try this yourself, and then resume the video to check your answers with mine. Find all factors of 5 factorial. Remember that 5 factorial is equal to 120. The factors are 1, 2, 3, 4, 5, 6, 8, 10, 12, 15, 20, 24, 30, 40, 60, and 120. How many factors does 6 factorial have? Well, 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. We could rearrange all the prime factors to put this in canonical form as 2 to the 4th times 3 squared times 5. So the number of factors is 5 times 3 times 2, which is 30. You may want to pause the video one more time and really look at this and make sure you understand where this is coming from. As a hint, focus carefully on the exponents in the prime factorization of 6 factorial. For n greater than 2, since n factorial has more than 2 factors, it cannot be prime. For example, 3 factorial has 4 factors and 4 factorial has 8 factors. Observe that when we add 1 to 3 factorial, we get 3 factorial plus 1, which is 6 plus 1, or 7, an integer that is not divisible by 1, 2, or 3. Similarly, when we add 1 to 4 factorial, we get 4 factorial plus 1 equals 24, plus 1 equals 25, an integer that is not divisible by 1, 2, 3, or 4. In general, n factorial plus 1 is an integer that is not divisible by 1 through n. Recall from exercise 4.9 that every integer greater than 1 has a prime factor. That's exactly what exercise 4.9 said. Every integer greater than 1 has a prime factor. As another exercise, let n be any positive integer greater than 2. Explain why there is a prime number larger than n. Go ahead and pause the video and try this exercise yourself using the information on this slide, and then resume the video to check your answer with mine. Let capital M equal m factorial plus 1. As we have just seen, m is not divisible by 1 through n. By exercise 4.9, m has a prime factor q. Since q cannot be 1, 2, 3 all the way through n, we must have q greater than n. Okay, so exercise 4.17 tells us that there are infinitely many prime numbers.